Welcome to Lecture 4, Measures of Disease Frequency and Association. I am Teresa Stack, an Assistant Professor for Montana Tech at the University of Montana, and this is a lecture in the series of Occupational Epidemiology. And so our objectives for today, we will do some plotting, look at some graphs so that you can understand the use of descriptive statistics in terms of describing person, place, and time again, and also start to become familiar with some of the three kinds of frequency measurements that are used to describe two category variables, also called dichotomous variables. And these are rates, proportions, and ratios. We'll also introduce some new terms, which would be the terms of incidence and prevalence. And so as far as preparing yourself to do assignments or the exam or just understanding the way data can be displayed to you and interpreted, I think that understanding the difference between a rate and a ratio and a proportion is important, and it gives you a way that you can take a closer look at the data and really figure out what's going on. And so you've probably heard of fatality rates, death rates, birth rates, ratios of success of a new drug, and we'll start to look at what that means in terms of epidemiology. So this would be one of the lectures where if you were keeping a equation sheet or formula sheet, that you might want to write down some of these formulas so it's easy for you to remember and you don't have to go back through and look at the PowerPoint slides again. So remember, there are two broad categories of epidemiology: descriptive epidemiology, which is concerned with the distribution of disease as categorized by time, place, and person, and these use our descriptive statistical terms and our measures of disease frequency, versus our analytical epidemiology, which focuses on the determinants of a disease by testing a hypothesis. That hypothesis is generally formed from analyzing our descriptive statistics. And so one measure of disease frequency is simply mapping. And I really like the topographical maps that are done by colors, or some people call them relief maps, because it gives you an indication of where the hot zones are by the density of the number of deaths in a given area. Other maps of measuring disease frequency, we can see mapping of the United States by the density of asbestos-related deaths from 1979 to 2001. And when you superimpose this with a shipyard map and the number of asbestos-related shipyard maps, you can see that it lines up pretty well and makes sense with the rest of the mapping of the United States, because asbestos was so widely used and is still part of many Navy vessels that are out there. You have, oh, I need a pen. So Puget Sound area, there's a naval a shipyard there. Norfolk Naval Shipyard, there's one in Virginia. There's another shipyard up in Maine. And we kind of have a cluster here. There's many Navy bases along the coast of California, although there aren't any shipyards in that particular area, Hawaii and Alaska. So this is a way in which we're trying to describe our data. So this is just simply one variable. It's just the number of deaths. But if our data sets, our maps, or our graphs, I should say, are labeled appropriately, they tell us something about time, place, and person. So our time was 79 to 2001. Our place was the United States. And the person was the persons who died from asbestos-related exposures. Time, place, and person. Other measures of disease frequency, where we start to plot the numbers across time instead of just a cumulative representation of the data. A cumulative representation of the data, plotting the measures of disease frequency over time. Ratios and rates and measures of disease frequency are simple statistics in their account of the number of events that occurred, cases of influenza, deaths from asbestos, cases of measles, and if we can get a grasp on the number of people who could have possibly been exposed over the number of people who are exposed, our data starts to make more sense. So they're just simple counts of the distribution and the determinants of disease. But what's really necessary, and it's one of the hardest variables to get your hands around in epidemiology, and I just believe in all sciences, is the denominator. And that's the size of the population that could have been affected, or the size of the population in which the source data was pulled from. So it's just simple counts, in a sense, and different ways of looking at the data, which influences how you interpret the data. So here we have broken down by demographic, which is our age group, and a simple count of the number of influenza season-to-date occurrences in 1 week, through the week ending December 1st. So if you didn't listen to the lecture or you don't remember me saying so, influenza is a reportable condition, and when any physician has a confirmed case of influenza, they call the public health department. And the public health department should, if they are a good public health department, then call the index case and make sure that other people who are susceptible to maybe developing pneumonia after getting influenza. So you have older seniors, people with compromised immune systems, or young children who haven't been able to get the influenza vaccine yet, that the case understands that these people are highly susceptible to getting the disease in a more severe form, and that they should be informed as well. And so this is a reportable case, and that's why it's week 48. Every week we would have to call our numbers into the states. So we're going to talk about rates, ratios, proportions, incidence, and prevalence. So before you learn about specific measurements, it's important to understand the relationship between the three types of measurements and how they differ. All three measurements are based on a simple formula, which is x over y, and that would be how we describe a proportion, x over y, or a ratio, or it's another way in which we describe a ratio. We use x with a semicolon y. Descriptive statistics allow us to understand a set of variables. And because it's a simple proportion, we usually only have two variables in which we're trying to describe. And I think if we take a little closer look at the example, it'll help you understand the difference between a ratio and a proportion. So the ratio of girls to boys is 1:3, or written 1:3. And this is also called odds notation when you write it this way. Or when we write our proportions, we could say 1 out of 4 children are girls, and that would be 25%. Now this becomes our proportion when we write it this way, or a percent. 25% are girls. Or we can say 3 out of 4 children are boys, or 75%. The proportion is the ratio where the denominator, where a proportion is a ratio where the numerator is included in the denominator. So a proportion has all 4 children, all of our population, versus the ratio, all of our population, versus the ratio of girls to boys. 1 to 3. That's our ratio of girls to boys. Our ratio of girls is 1 out of 4. 25%, we turn it into a percent by multiplying it by 100. So here's another example, and it is really quite difficult to teach math-related subjects and not be live in front of you with a whiteboard on a screen, but I'll do my very best. So if we had a population of 35 people and 15 of them were men, we would know that 35 minus 15 is 20. So 20 are women, right? So what's our ratio of men to women? Our ratio is 15 to 20. Or our ratio can also be written as a fraction, 3 to 4. We're just reducing our numbers down to their lowest, simpler, or lowest common denominator. Or you can say for every 7 people in this group, 3 are men and 4 are women. So we took our 3/4 and we added it together. 3 plus 4 equals 7. After we took our fraction and reduced it to its lowest common denominator, and then we just describe it again. For every 7 people, 3 are women and 4 are men. When you break it down this way, it's a lot easier to get a handle on than for every 35 people in this room, 15 are men, 20 are women. So it's a way that enables you to more clearly see the data and be able to describe it. So I'm going to give you, I guess you could just pause, so I didn't have to pause here and give you any time. But another example so that you can get your hands around calculating ratios and what they mean. The ratio of passing grades to failing grades in this epidemiology class is 7 to 5. How many of the 36 students will fail the course? Now certainly, I hope the ratio of passing to failing grades is more in the area of 20 to 1. Okay, so first we write it as a ratio. 7 pass and 5 fail. So that's 7 plus 5 equals 12. Out of 12 students, 5 fail. When you're doing epidemiology or any kinds of statistics, remember finally, or remember what you are trying to get to. What's the final number that you're trying to get to? So we want to know how many of the 36 students will fail. So we're trying to find our failures. So out of 12 students, 5 will fail. That is, 5 out of 12 will fail, 5/12. We take this number and we multiply it by our population, our 36, and we find out that 15 people will fail. So of our 36 students, 15 will fail, which means 21 people pass the course. proportions. A proportion is a specific type of ratio in which the numerator is included in the denominator. A fraction with the numerator on top and the denominator on the bottom can be multiplied, of course, as a percent if we simply multiply it by 100. A proportion can be used, was used when we calculated our attack rates. We also call this our cumulative, it could be used when we calculate our cumulative incidence. So I think that's another part of epidemiology that can be kind of chewy, for lack of a better word, are the different terms. The difference between a ratio where the denominator is not the total population, but if we add those two numbers together in a ratio, we get the total population. A proportion is that all the numbers that are in the top, all the cases that are in the top, are also in the bottom as well. And of course, when we multiply it by 100, we get our percent. So the proportion of all births that were male. So we have all births, which would be our males and our females. What proportion of them were males? 51%. All right. So we talked about ratios and we talked about proportions, and there are more examples to come. Now we're going to talk about rates. A rate is a special form of a proportion. So in a rate, remember again the difference is that the denominator includes the information that was in the numerator as opposed to a ratio, which does not. A rate is a special form of a proportion that also includes a specific time. It can measure an event, a condition, an injury, an illness, or a disability within a certain time period. Chronic occupational exposures, it's challenging to determine a specific time period when you have a really long exposure period. So, for example, it took 30 years for mesothelioma, or it takes up to 30 years for mesothelioma to completely manifest itself in many people. Some folks, of course, depending on their dose, it comes on much faster. Because the rate, the exposure period is so long, it's really difficult to specifically say that it was only the occupational exposure that caused the disease. Now, in something like asbestos, unless you were living in Libby, Montana, where it was flying out of a mine and it was a public health concern as well as an occupational concern, you can narrow down that you could narrow down the contaminant for asbestos. So we took our proportion, our males, and we added a year, and now we're able to turn it into a rate. The proportion of all male births the proportion of all births in 2013 that were male, our proportion simply became the rate. Okay, so let's go back to our ratio example one more time. And what I think you should do is maybe pause it and see if you can solve the problem without looking at the next slide. Consider the men and women at a party. See, now it's a party. Haha, it's fun, right? Epidemiology is fun. their ratio is 15 men to 20 women, right? We have seen this ratio before. Suppose the party grew and there were now 56 men. How many women would there be? Okay, so when we look at going back to our rate, we have our numerator, which is the number of cases. The denominator is our total population. The numerator is a subset of our denominator. And because it's a rate, we know that there's a specific time period related to it. And a lot of times we have it as a unit size, so it would be 1 death in 2013 related to rabies bites per 100,000 residents. And so we start to add that variable k on the end of it so that our numbers are more reasonable to work with. And it also allows us to do a comparison. So at what rate are you accumulating speeding tickets? So this would be the number of speeding tickets since you started driving and the years since you started driving. So do some math, see what you came up with. And I thought this was really interesting because I've been driving since I was 16 and I'm now 47 years old, so that's 31 years. And I've had 10 tickets in 31 years. So 10 tickets in 31 years is 0.32 tickets per year, or an average of 1 ticket every 3 years. If we wanted to adjust this rate, we could do that and adjust it by looking at when you had the highest density of your speeding tickets, which was probably in the beginning of your career. So there are different types of rates. There are crude rates, which is the actual number of events in a population. It's unadjusted. Number of dog bites treated in the ER where tetanus was given in 2014. We would need to know that. Stratified specific rate compares a specific population. A lot of times when we stratify our rates, we stratify them by age, we stratify by gender, we stratify by location. So if we're going to give you a stratified rate, it would look more like the number of dog bite cases who were between 1 month and 2 years old treated in the ER where tetanus was given. We're trying to take our total number and stratify it by our specific demographic. And our adjusted rates, it takes a little bit longer to do an adjusted rate. So in an adjusted rate, we try to make all things to become equal. If we had 14 dog bites in Montana, would that be the same rate as 14 dog bites in Florida? What's the rate at which they're occurring? Well, actually, our population in Montana is much lower than it is in Florida, so people would be getting bit more frequently in Montana than they would in Florida. So a way we'd be able to adjust this or normalize the data is to recalculate it and account for that inequality. And we do this by the distribution of age, sex, number, race, or some other variable. So the number of dog bite cases who were between 1 month and 2 years old treated in the ER where tetanus was given between 1999 and 2012, and we adjust it to the 2012 census, meaning that we adjust our denominator number in 1999, 2000, 2001, all the way to 2012. We adjust that denominator so that we're able to compare did we actually see an increase in our rate of dog bite cases, or a decrease, let's hope, from 1991 to 2012? If we just take our crude rate, we're not quite sure if we're seeing an increase or not, because our D, our denominator, our population, would change over time. So these are, again, different types of rates. When you see crude rates, these are just a number. They have not been adjusted. When you see a stratified rate has been stratified or separated because of some particular variable in the population that we would like to pull out. And we can stratify by a whole bunch of different types of variables. And an adjusted rate is not the true rate. It's a recalculation of the rate to account for some other kind of distribution. Age and gender-specific motor neuron disease mortality rates within 5-year intervals. So here we are stratifying the data by which variable? Gender and age. This is your person. If we said, oh, this is your place, and this is your time. Person, place, and time. Or we could stratify by race. Now we took our male and female population, combined it back together again, and decided to stratify by race. And we certainly see that a difference between our white and our black population, and then another group population of other. Please just know that I try to make this as simple as possible. If you're in the other category, I don't mean it in a bad way of any way, by ethnicity. And there again is when we're adding on our unit per 100,000 people, so that our numbers are more manageable. They're much easier to look at. So again, we have our person, our place, our time, and our rate. So what's the ratio of black deaths to white deaths? Our ratio would be correct? And how about our proportion? So the reason why epidemiology, or really any data set, although we're talking about epidemiology, it isn't only in epidemiology that we try to stratify our data, but we do try to stratify our data to see if there's one variable in particular that's driving our data up or down. And it's really useful to help in targeting where we should put our interventions in place. So now we're going to look at another topic, and the next topic will be adjusting rates. Another way to present rates is to adjust them for some type of variables. This allows us to make a fair comparison. So what are they adjusted for? Crude rates are the number of cases of disease per 100,000 people, stratified by male and female. And then if we adjust them to the 2012 census data, or this would be, I'm sorry, if we adjust it to the 1998 census data, then we could make a clear determination of whether there's actually an increase or a decrease in our crude rates or in the rate in which the disease is occurring. So for example, did we have a higher percentage of males that were born in 1969 than we do in 1979? So we tried to adjust this to make up for the difference in your male versus females. So when you look at the graph, looking at first that dotted line and then looking at the solid line, you can see that when we adjust for the differences in the proportions of the populations of males to females over time, that the number of male deaths decreased from the crude rate and the number of female deaths increased from the crude rate. So when we adjust our data, it shows us something significantly different than our unadjusted data. And I'm sorry, this is the slide. I said it in the previous slide, but this is a slide where the annual adjusted cancer rates from 1975 to 2007, the rates were adjusted, that denominator, the bottom number, to the 2000 U.S. census populations to normalize the data a little bit more. What do you see? We have some good screening programs in place now. Decrease leveled out. Nice decrease. Increase. And this one always surprises me, because we have an increase versus a decrease. What questions do you wonder when you look at the data? Why is there a difference? All right, we're going to talk about the terms of prevalence and the terms of incidence. Prevalence is the proportion of individuals in a population who have a disease at a specific point in time. And it depends on two things: the number of people who get the disease and the duration of the illness. So if you have a disease that has a very short illness, for example, Ebola, once people in South Africa broke out with symptoms, within 14 to 21 days they would pass away. So the prevalence was low because the duration of the illness was so short that in a year's time people didn't have the illness anymore because they had passed away. So the dynamics of prevalence can be represented by fluid filling a basin. Water, which is your incidence rate, is continually flowing into the basin, and the basin drains through the outlet. The inlet of the water represents incidence. Incidents are new cases that occurred within a certain time period, while the outflow represents your resolution, whether you have passed away or you've recovered. The water level represents the prevalence of a disease in a population. The increase in prevalence can result from increases in inflow, that's an increase in the number of incidents, or the increase in prevalence can occur if you have a decrease in the outflow. So for example, the prevalence of HIV in our society today is about the same as it was in 1985. In 1985, you had a huge influx. You had a large incident rate of HIV being diagnosed. And so our prevalence rates went up. Now we have very few, I wouldn't say very few, but much lower incidence of HIV, new cases occurring every year. But our prevalence rate is staying the same because people aren't passing away from HIV as rapidly as they were in 1985, before the disease was fully understood or we had a way to treat the disease. Prevalence is the proportion of individuals in a population who have a disease at a given time. And it's related to the incidence, which is the new cases coming in, and again, the duration of that disease. Although that's not what's used in the calculation. So again, this is another calculation. That's prevalence, prevalence being a proportion, the number of existing cases over the average population at a specific time period. Now we say the average population unless you're able to actually get a count. So if you were taking the prevalence of hearing loss in your company in 2015, then that would, you actually would still have an average population, the average of what the population was, the number of workers that you had in the year. It wouldn't be a specific population unless that population didn't change over time. But because the population changes over time, we take the average. So we need a measure of the number of cases at a point in time or a time interval, and a measure of what that population is. And I like the slide. It just is really, I think you're really able to see what's going on here. So in A, the level of prevalence in a population. In B would be an increase in prevalence resulting from an increase in incidence. C is a decrease in prevalence in our population because of deaths or cures. And D would be the overall impact of prevalence because of our incidence rate and our deaths and our cures. There's two types of prevalence. There's point prevalence, that's at a specific point in time, and there's period prevalence, prevalence of a disease, disorder, or event over a range of times. So a point in time over a range in times. Point prevalence. Do you have asthma now? Period prevalence. Have you had asthma in the last year? Cumulative incidence. Have you ever had asthma? Incidence would be new cases. Cumulative ever. Period last year. Point right now. So here's our example of point prevalence. What is the point prevalence? So these are all cases. So we have 1, 2, 3, 4, 5, 6, 7, 8 possible cases. Out of these 8 people, how many people had the disease on May 2nd? And that's what this red line represents. So see if you can figure out what the point prevalence is. So if you died, you are not part of the data set. Your point prevalence is 5. Oop. I thought I explained that on the next slide. Sorry about that. There it is. The next slide. Oh, see where I made the mistake? I gave you a rate, 5 out of 8, instead of our total population was 500. Should have been 5 over 500 is your point prevalence. I gave you your prevalence rate. Sorry about that. So the number of existing cases, was 5 out of 500 people. Your point prevalence rate would be 0.01. Period prevalence is through a time period. So assuming you had the population for the entire, assuming you had the records for the entire population, what is the period prevalence for January through September? So what is your period prevalence? We still need an average population, which we would do specifically by adding your numbers and dividing. So what's your period prevalence? Eight out of 500, or 0.016. 16 prevalent cases per 10,000 population from January through September. We count everyone who was or is still a case within that time period. And therefore, with prevalence, people can be counted twice. So for example, in your state, what's the prevalence of influenza? If one person had it 3 times, that case would be counted 3 times. I hope you enjoyed our discussion of ratios. One out of 4 of us is fishing. The proportion of people who are fishing. Incidence would be our number of new cases in a year, and prevalence would be the number of cases in a year. Rates, ratios, proportions, incidence, prevalence. Have a great day.